So, a very good afternoon to all of you. And if you rightly go back, yesterday we talked about the basic postulates of modern quantum mechanics, and we tried to talk about these postulates point by point. And today, my target is basically superposition principle, because superposition principle is the beat of the universe. We find superposition principle everywhere. And before going into the details of superposition principle, I would rather take an imaginary example to get the feel of this superposition principle. Because we have superposition principle in the classical physics also, and we have superposition principle in quantum physics also. But the superposition principle that we have in quantum world is a little bit strange. But the idea is same. So to start with, if I imagine that there is a boy, and the name of this boy is, say for example, his name is Rahul. He is a musician and he knows how to buzz a flute. You know the flute? And there happens to be another boy, let us assume his name is Ahil. One is Rahul and another is Ahil. And Rahul is a very good musician. He knows how to bang a flute. So whenever he bangs a flute, Ahil comes and he tells him, "What are you doing? How you get all these strange, mesmerized, symmetrical music? Can you train me about it? Can you teach me how to buzz it, how to use it, how to produce the sound?" So Ahil goes under training. He learns how to use a flute and produce the symmetrical sound. Now what happens? Both the guys use the same instrument. When they use the same instrument, the room bangs. The room bangs at times, and at times there is calmness in the room. So what's happening? What's happening here? The boy who has learned how to use this flute, he again comes up with a question. The question is that we too are using these instruments, but the whole of the room is banging, and at points you find that the music is going high, and at points we find that the music is going low. Assuming that Rahul is a physicist, he tells him that when I use the flute, it produces sound waves. When you use the flute, it produces sound waves. These waves superimpose. And when they superimpose, there are chances that we can have a situation in which the two waves will superimpose so that you have a maximum. And there are the chances that the waves can superimpose where you can have a minimum. So it is the play of the waves. It's the waves that are superimposing on each other. Now, depending on their nature, they can produce the waves of high intensity and they can produce the waves of low intensity. And Rahul, assuming him to be a teacher, he tells Ahil, go to the lake, take the two pebbles in your hands and see how it happens. Because he couldn't see the sound waves. So the boy Ahil goes, he takes a pebble, drops it into the water. There are waves, he drops another waves, and what he finds somewhere the level of the water is high, somewhere the level of the water is low. And to be frank enough here, the universe goes like this. In universe, you only find superposition. And superpositions take us to high intensity, they take us to the low intensity. They take us to the intermediate intensity. Now, you cannot fling yourselves to that level alone. You can extend it to the humans as well. Humans always produce these superpositions. We have an interaction. This interaction is creating a superposition between you and me. Then you will go back home, you will have an interaction with your family. You will have another superposition. In every case, you will have a maxima and minima. Somewhere you may agree, somewhere you may not agree, somewhere you may be in intermediate state. So this is our classical superposition. And quantum mechanical superposition is a little bit stranger, but the idea is same. You have the superposition of the complex waves. You have the superposition. Mathematically, you are doing it that way. But it's strange here. The strangeness comes if I again go back to the double slit experiment. Because double slit experiment is an example of understanding the basic nature of quantum mechanical superposition. Here again you have the superposition of the waves. Now if I go back to the double slit experiment, what is happening? If I shoot the electrons through both the slits, I will find an interference pattern. Nothing wrong with that. You will say, come on, electron is behaving like a wave. But when I reduce the number of electrons, if I shoot one electron in 1 second, what is happening? You expect that electron is a particle. And now, if you are not looking at the experiment, and you are shooting electrons one in 1 second, after, say for example, after 100 years, you will see the interference pattern. You will have an interference pattern. But the moment you will look at the experiment, looking means you will see through which slit the electron will go. Now what electron does? Electron behaves like a point particle. When you look at the electron, it goes either through the slit 1 or it goes through the slit 2. But before observation, what was there? There was superposition. Before observation, electron was behaving in a totally different manner. When you were not looking at the experiment, it was behaving like a wave. That's why you have interference pattern. Even if you shoot one electron in 1 second. The same example goes with Schrodinger's cat. The double-slit experiment is a very beautiful extension of Schrodinger's cat, because cat looks so big to us. So a cat in a box can either be dead or alive. Is it just an argument? Is it just an argument about an electron? No, it's not an argument. It's a reality. Let's try to understand the difference between the probability that you do in quantum mechanics and the probability that you do in classical physics. What is the probability in classical physics for a dice? I will shoot a dice. What is the probability of getting 1? You will say, sir, it's 1 by 6. What is the probability of getting 2? You will say it's 1 by 6. Or if I choose a coin, what is the probability of getting a head? Now, if I talk about the quantum mechanical probability, can you answer this question? If you shoot a dice, what is the quantum mechanical probability for this context? Yes, can you answer this question? Now here the probability is different. There's a probability that you will have 2 heads for the same coin. There's a probability that you can have 2 tails for the same coin. There's a probability that electron is at both the slits at the same point of time. But the only thing is that you don't have to look into the experiment. If you will look into the experiment, it will behave as a coin. It will behave as a classical probability. It will behave as a classical particle. So when you look onto this quantum mechanical system, the quantum mechanical system behaves in a different way. But when you don't look at it, it behaves in a very, very weird quantum mechanical way. And it's a reality that it is behaving like this. Because if it is not behaving like this, then you cannot have a quantum computer, at least in its initial state. Are you getting my point? Are you able to differentiate the quantum mechanical probability and the classical probability? Okay? So that is the difference between the probability that's why the superposition in quantum mechanics is more strange. Otherwise, when you use superposition principle in the classical sound waves, electromagnetic waves, you have the results of maxima and minima. But here you have a strangeness. Your one electron can be at many positions at one point of time. Are you getting it? Okay. So what we would like to write down this superposition in a mathematical form. So what is the target? The target is to discuss this superposition. Come on. I don't know what am I writing. Okay. Now, if you go back to yesterday, we started with a state vector. And what's that state? Say that state is psi. Right? And it's a ket of psi. And this psi you can write as a combination of. You can write it as a combination of linear vectors. So what does that mean? How can I go to the next page? This? Okay. So, I have a state psi. This state can be a combination of many states. Because this psi belongs to a vector space which is known as Hilbert space. right? So this ket of psi can be written as, say for example, alpha 1, say phi 1 plus alpha 2 and phi 2 plus so on so forth, right? And this state psi can be written as a summation of alpha I, phi I. This equation is giving you a mathematical description of superposition. So you can write down a state vector as a linear combination of n number of state vectors. Okay? Where alpha 1, alpha 2, alpha 3, alpha n, they are all the coefficients, and we calculate these coefficients using normalization condition. So what does that mean technically? That means that your state is right when the sum of these coefficients, the squares of these coefficients, will be equal to 1. What's that? That's the probability, right? So here I have a state psi. I can write it as a linear combination of phi's, okay? And this psi belongs to a vector space known as Hilbert space. Is this clear? Okay? Now let's understand this. And we will understand this using an example. Okay? So that will be the right choice. Okay. So can I rub it directly? Or? Huh? By hand I can rub it. It's not happening. Come on, this one, please. Okay. Now what I have a state psi. I have a state psi, and this psi is a linear combination of under root of 3 by 3. Under root of 3 by 3, say zeta 1 plus 2 by 3, say zeta 2 plus root 2 by 3 and zeta 3. Okay? You have a state psi, and this state is a linear combination of these three vectors. And the question is, I want to first normalize this state. I want to prove that this state is a normalized state. How can I prove that? This should be my first question. That this state that I'm writing here on the board, it's a normalized state. So how can I do that? But this board is very freaky. So, okay, what will I do? Before, have you written down this? Okay, tell me the values if I need them. Now see, you have a state psi, okay? Now, this is called a ket. It's a ket. And it has a bra like this. The difference between ket and bra is you have a wave function, say psi, it has a complex conjugate. For a ket, you have a complex conjugate. This is known as Dirac notation of state vector. Okay, so this is the same kind of thing, but here you can accommodate different kinds of situations, right? This ket can be a column vector.
this ket can be a simple function, right? So that's why it's more fundamental than that of the wave function that you have been using till now. So what am I telling you? This is a ket. Corresponding to every ket there is a bra. Okay? So if you remember that integral, psi star psi dx, what is this equal to? 1. Isn't it? Right? So if I have the ket of psi and I have the bra of psi, this will give me 1. Are you getting it? Okay. Now move on. So now what I have, if I have psi and phi, this will give me 0. Because they are orthogonal to each other. So these two important conditions are needed. Okay? Now let's go with the first condition. I have an equation. Can you tell me what is that equation? That is this equation. Okay? This is my equation. Okay? And I want to prove that this state vector that I have given here is a normalized state vector. So for that, what I will do, I will multiply each part in this equation by its corresponding bra. So if I multiply each part in this equation by its corresponding bra, what will happen here? You will have psi here. What will happen here? You will have zeta 1 here. What will happen here? You will have zeta 2 here. What will happen here? You will have zeta 3 here. Are you getting? Okay? So this will give me 1, this will give me 1, this will give me 1, and this will give me 1. You check in the right hand side what you have. Root 3 by 3, 2 by 3, and root 3 by 2. Okay? Come on, give me those values now. Yeah. So what I have psi and psi. This is equal to what? Come on. Loud. Under root 3 by 3 plus under root. No, it's not. There is no root. This is 2 by 3 plus under root 2 by 3. Can you see this? If I write something like this, what is it? It's the probability. It's the probability density. Okay? So probability density P is equal to the square of this. This is already calculated. So probability density is under root of 3 by 3 plus 2 by 3 plus under root 2 by 3 whole square. Right? So what will be inside? P will be square and root will cancel. So this is 3 by 9 plus this is 4 by 9 plus this is 2 by 9. Get it? So this is 3 plus 4 is 7 plus 2 is 9. So this is 9 by 9. What is that equal to? That's equal to 1. What does that mean? That means the state vector that I have given you is a normalized state vector. Right? This is the one way of doing it. Now the next question could be, what is the probability? What is the probability for having a state psi 1, zeta 1? Where is it? Now the next question is what? Probability of zeta 1. Okay? Again, tell me the state. State psi is equal to, come on, under root 3 divided by 3. No, tell me the state. It is zeta 1 plus 2 by 3. This is zeta 2 plus under root 2 by 3 zeta 3. Yeah. Come on. Okay. So what I need zeta. Suppose I want the probability of finding the particle in this state zeta 1. For that, what I will do? I will multiply this equation by zeta 1 from left. Okay. So what I will have zeta 1 and psi equals, this is under root 3 by 3. So it is zeta 1, am I right? Plus 2 by 3. It is zeta 1, zeta 2 plus under root of 2 by 3. Yeah, zeta 1 and zeta 3. Are you getting? So you immediately understand that this is equal to 0. Right? You understand this is equal to 0. So what you are left with? You are left with this term. So zeta 1 and psi will lead us, it will lead us to what? Under root 3 by 3. Zeta 1 is what? That's 1. That is 1. So what I want to calculate the probability. I want to calculate the probability of zeta 1. What will be that? That will be zeta 1 psi whole square. So what will be that? That will be under root 3 by 3 whole square. So that will be, square and root will cancel. This is 3 by 9 and that is 1 by 3. This is the first part. Okay? Now I want to calculate the probability of zeta 2. Now let's go fast. Come on. Let's go fast now. Come on. So for zeta 2 I will multiply by zeta 2 to my state psi. That will, the first term will die. Okay? The second term will exist. The third term will die. So what is the second term?
2 by 3.
This is 2 by 3 and zeta 2 and zeta 2, and this will give us 2 by 3. But I want to calculate the probability for zeta 2. That will be zeta 2 psi whole square. So that will be 4 by 9. Am I right? Now the last part is what? Zeta 3. Okay? So for zeta 3, you will have, Derek, tell me what you will have. First term will die, the second term will die, the third term will exist, and you will have under root 2 by 3, and then you will have zeta 3 and zeta 3. But this is normalized, so this is equal to 1. Okay? So I can calculate can I move on? So I can calculate the P zeta 3 is, how much was it? Under, it has to be zeta 3 and psi whole square. Isn't it? But what was the value? Under root of 2 by 3 whole square. So this is 2 by 9. Okay? So you got 3 probabilities. Probability of, say for example, probability of particle to be in state zeta 1, to be in a state zeta 2, to be in a state zeta 3. So let me add the 3 probabilities. Zeta 1, P, zeta 2, P, zeta 3. What was zeta 1? 1 by 3 plus 4 by 9 plus 2 by 9. So this I can write, This I can write 3 by 9. Can I write? Oh, can I do it? Come on. 3 by 9 I can write it. It has a problem. Okay? So you can see what is happening. You have 9 by 9 equal to 1. So what it is telling you mathematically, this problem? This problem is mathematically telling you that your state psi is a linear combination of the states zeta 1, zeta 2 and zeta 3. Now these zetas, they are the realities. They are the realities. That means if I have a particle, this particle can be in state zeta 1, zeta 2, zeta 3 with all the 3 probabilities that you calculated. And the sum of all the 3 probabilities that you have calculated is equal to 1. It's clear? You got the idea? Okay? So my intuition was to tell you that quantum mechanical superposition principle is it has the same basis as that of the classical superposition, but it's a little bit strange. And the strangeness can be seen by solving this problem. And what we understand is that your state vector psi can be written as a linear combination of many state vectors, provided all the state vectors and the state vector you started with belong to a vector space which is known as Hilbert space. If you have any questions, you can ask me.